Okay, good afternoon, everyone. Thank you all for coming. My thesis topic is QoS routing and mission control scheme for wireless ad hoc networks. This work has been done under the guidance of Professor Michael Gritzer. Okay, this is outline of my presentation. In the first part, I'll give the motivations and the challenges of this work. And the second part, the overview of our solutions is given, and followed by the background of our work. And I'll explain the QoS routing and the mission control scheme we proposed in details in the fourth part, followed by protocol implementations. Simulation results and object demo are given in the last two parts. With the increasing use of wireless ad hoc networks for delivering real-time traffic such as video or audio or multimedia, quality of service becomes increasingly important. Such kind of traffic has some specific QoS requirement to be satisfied, such as minimum bandwidth, maximum delay, or some loss requirements. So in this work, we addressed three questions. The first one is how to avoid the congestion. This is important because no QoS guarantees can be provided if congestion occurs in the network. And the second question is how to find an end-to-end path satisfying the QoS requirements. And also, we address how to increase the channel utilization while maintaining some level of quality of service. Due to the characteristics of wireless ad hoc networks, there are a couple of challenges in providing QoS in the wireless ad hoc network. There is no fixed infrastructure, no centralized control. So any QoS scheme should the QoS scheme should be distributed, and also since there is scarce resources, the QoS scheme should not introduce too much overhead. And also the biggest challenge comes from the shared nature of wireless channels, which I'll explain in the next few slides. So to address the mention the three questions, our solutions mainly consists of three parts. The mission control is used to control traffic load and prevent the network from reaching the congestion point. QoS routing is used to find an end-to-end path between sender and receiver, which can satisfy the QoS requirements. It can also lead the traffic go around the heavy loaded areas. In these two parts, we consider an extended contention range, and also when we calculate the bandwidth consumption of flow, we consider the feature of location dependence. In our work, we exploit parallel transmission to increase the channel utilization while maintaining the quality of service. Now I'll give some background of our work. As we have known, there are two important distances for packet transmission and reception. Transmission range is maximum separation for successful packet reception, and all the nodes within the transmission range of a particular node are called its neighbors. And the second range is Kerosene range. Kerosene range is the maximum separation for a node to detect an ongoing transmission. Typically, Kerosene range is much larger than transmission range. So if a node falling outside the transmission range, but within the Kerosene range, it can sense the signal, but it cannot decode the packet. In CSMA-based MAC protocol like 802.11, all the Kerosene neighbors cannot initiate transmission while the sender is transmitting. In the example we give here, if A is a sending node, then B is A's neighbor, one of A's neighbors, and C is one of its Kerosene neighbors. So although C cannot communicate with A directly, it cannot transmit at the same time as A does. So this is called the shared nature of single-channel wireless communications. So in multi-hop ad hoc networks, the shared nature implies 4 things. First, when we consider the contention around the node, we need to consider an extended contention range, not just the transmission range. Also, the contention is location-based. For example, the node in the network center will face much more contention than the edge nodes. And also we need to consider intra-flow contention when we calculate the bandwidth consumption of at a given node. For example, if there is a path from A to D through node B and C, then whenever B is transmitting, it will contend for the channel with A and C. So that means transmission from node A and C will consume the bandwidth as node B. So we need to consider this when we calculate the bandwidth consumption. And also we notice that a load outside the carrier sense range of a node can transmit at the same time as this node. For example, there's a node D, which is outside the carrier sense range of A, so A and D can transmit at the same time. We explored this feature to increase the channel utilization in our scheme. What is the quality of service? Simply speaking, QoS is performance level of service a network provides to users. The goal of any QoS mechanism is to provide applications with guarantees in terms of bandwidth, delay, or jitter, so that information carried by the network can be better delivered and the resources can be better utilized. QoS routing is a process of providing end-to-end paths to guarantee necessary QoS parameters. And admission control is a necessary component to support QoS. And it's the process of deciding if a new user can be granted service or not. Now I'll explain our QoS routing and admission control scheme in details. First, we need to a node needs to estimate the unused bandwidth so that it can determine if can accommodate this flow or not. So due to the shared nature of wireless channels, unused bandwidth at a given node is affected by its carrier sense neighbors. And this means when a node estimates the unused bandwidth, it needs to consider all the transmission activities within its carrier sense range, not just the transmission range. So maybe there are some nodes which cannot directly communicate with, but the admitting node leads this bandwidth information. And the second is transmission from the node itself affects the unused bandwidth of its carrier sense neighbors. And the second point means that when a node make an admission decision, it should consider not only the local unused bandwidth, it also needs to check the unused bandwidth of its carrier sense neighbors because it must ensure admitting this new flow should not degrade the quantity of service of flows going through its carrier sense neighbors. So there are 2 terms we need to estimate. One is the local unused bandwidth, and the other one is unused bandwidth of its carrier sense neighbors. To explain the importance to consider the unused bandwidth of the node's carrier sense neighbors, I give a very simple example. Here, A and E, both A and E are those C's carrier sense neighbors, but A and E cannot sense each other. So when the first flow from A to B starts, and the bandwidth at node A and C will decrease to 1.07, and after the flow 2 starts, the bandwidth at A and C and E will decrease. Here, the A and C's bandwidth decreased to 0.14, and E's bandwidth decreased to 1.07. And when later on, when node E wants to admit the flow 3 into the network, if it doesn't consider the bandwidth of its carrier neighbors, say load C, it will make the wrong decision to admit this flow into the network. But if that happens, load C will get congested. So this tells us how important when make an admission decision, consider the bandwidth of the load's carrier neighbors. In our work, we used the channel utilization to estimate the unused bandwidth at a node. In this formula, rho is the channel utilization, and B is the link rate, that is the channel capacity. We measure the channel utilization using channel busy time. During every measurement interval TP, we measure the time the channel is in busy state, and then we calculate the channel utilization and then estimate the unused bandwidth. Because we want to estimate both the local unused bandwidth and the bandwidth of its carrier neighbors, we need to measure the local busy time and the busy time around its carrier neighbors. So because the local channel utilization is determined by the transmission activities within its carrier range, so the node can estimate the local channel busy time just by simply monitoring the channel using the carrier threshold. But this information at node A itself cannot give it the information of bandwidth of its carrier neighbors. Like in this example here, A can use this carrier range, carrier threshold to get the local busy time, and node M4 can get the information using the same method. But when A makes the admission decision, it cannot know the information at node M4. So how does A know this information? In our work, we just use the passive method to increase the measurement range, and which is called the label carrier range, which covers the carrier range of all the carrier neighbors. So there's two measurement ranges, one for measuring local channel busy time, and the other for measuring the channel busy time at the node's carrier neighbors. And also, based on these two time measurements, we get the local unused bandwidth and the unused bandwidth of these carrier neighbors using this moving average formula. There is a very important fact we need to point out. The estimate of unused bandwidth at the load's carrier neighbors is very conservative in using this passive method, because we made the assumption that any transmission in a load's label carrier range will consume bandwidth at all of its carrier neighbors. Okay. After the node gets unused bandwidth, it should calculate the bandwidth the flow will consume. For 802.11 MAC using RTCT's data ACK 4-way handshake, per hop occupation time of data packet can be expressed as this formula. It includes the interframe space, RTS, CTS transmission time, the data transmission time, ACK transmission time, and the backoff time. Since our scheme is designed to avoid congestion, so we assume the collisions in the network is negligible, so we can assume the contention window remains the minimum value. So we use this last term to express the average backoff time. So if the application generates R packets per second, the bandwidth requirement W of the source should be R times T data times the link rate B. So how to calculate the bandwidth consumption at a given load on the multi-hop path? In this calculation, we need to consider intra-flow contention. That means on the same flow, transmission at each hop has content for the channel with upstream and downstream nodes. For example, in this figure, if A is when A transmits, it will contend for the channel with N1, N2, N3, and N4. So the bandwidth consumption at a node depends on its position on the path. We can say the node which in the center of the path will face more contention than other nodes. If we see the C1, the source of the flow, it can just contend for the channel with C2 and N1. But for A, there are totally 4 nodes contending for the channel with itself. So, we assume the contending nodes are within the Carrison's range of a node is N count L, and we can calculate the local bandwidth consumption using this formula, and also we can calculate the bandwidth, estimate the bandwidth consumption at the node's Carrison's neighbors using this formula. Due to the dynamic topology on stable channel conditions, the number of contending nodes are very hard to achieve. So in our work, we do the following approximations. We approximate the N count L as the number of nodes within this number of hops. The CSR is the Carrison's range, R is the transmission range. In 8 of 11 MAC, which works at 2 megabit per second, CSR is almost twice as the transmission range. So the N count L is estimated as the nodes within 2 hops of the given node. And because this neighbor Carrison's range is the neighbor Carrison's range covers the Carrison's range of all its Carrison's neighbors, so the NCSR should be twice as the CSR. So this number the N count C should be 4. So how, based on the bandwidth consumption and the unused bandwidth, how does a node make an admission decision? So here we give a very simple example. Because A and E are outside of each other's Carrison's range, so they can transmit at the same time. Flow 1 and flow 2 start first, and then node E wants to admit flow 3 into the network. At this time, it should ensure first the local condition, the channel utilization used by CD and EF should be less than 1. This is a local bandwidth condition. And second, it should ensure the carrier sense neighbor node C has the enough bandwidth. This should be row AB plus row CD plus row EF minus row overlap less than 1. Here, the row overlap is the fraction of A and E transmitted at the same time. So we should subtract this overlap part from this total channel utilization measured at this node E. So the node should ensure these two conditions to be satisfied so that it can admit a new flow. So this is a simulation, a simulation to see how much can be admitted with and without admission control. This is the network topology is this one, and this line is bandwidth consumption of flow A to B, and this one is the bandwidth consumption of flow C to D. So we can say if there is no parallel transmission consideration, at most only this amount of traffic can be admitted into the network. But if we consider parallel transmission, we can admit as much as around 1 megabit per second into the network. So there is a huge difference between the results with and without parallel transmission. And in general, if we assume the per hop occupation time of requesting flow is T sub R, then if this flow was admitted in the network, the local channel utilization and the channel utilization of its carrier sense neighbors can be expressed as these two formulas. We notice that in the expression of the channel utilization at the node's carrier sense neighbors, there is a row overlap part, and this is a fraction of time in which node A and the nodes within this light shaded area transmit at the same time, because all the nodes falling inside this area can transmit at the same time as node A. So we consider this parallel transmission fraction into our bandwidth calculation. So to avoid congestion, the admitting node A must ensure first the local utilization should be less than 1. This is very straightforward because the node can just compare the local unused bandwidth and the bandwidth consumption of flow to decide if the flow can be admitted. But because there is an overlap part in the second formula, we need to derive the general admission decision rule. By multiplying the link rate B on both sides of the second inequality, we get another inequality expressed in bandwidth. So, and finally, we get this formula. So the left side of this inequality is the bandwidth of flow will consume at the load's carrier sense neighbors, and the right side of the inequality, we can regard this right side of the inequality as the bandwidth actually available to the requesting flow. So if there is no congestion, this term should be always greater than 1. So we can admit more flows into the network with parallel transmission consideration. So how our protocol works? And first, we assume there are 3 flow wants to enter the network. The flow 1 will flood the route requests throughout the network. And in the route request packet, there are two fields related to the QoS routing. One is the W, which means the bandwidth requirement of the source node A, and the second field is the hops, which denotes the hops the route request packet has traversed. So this field is initialized to 0 at the source node. So this node. So when the intermediate node receives the route request, it will calculate the partial bandwidth consumption based on the upstream nodes, and then it checks bandwidth availability to see if it can admit and reject the flow. If the bandwidth can be satisfied, then it forwards the request packet and then set a timer in case the route reply packet does not send back in time. And if the bandwidth cannot satisfy the requirement, then it just simply drops the route request packet, and then this packet will go through all down to the destination. Once the destination receives the route request packet, it will do the same thing. Besides, it will, if the bandwidth can be satisfied, it will reserve the bandwidth, and also it sets a timer in case the real data packet does not come in time. And also it sends back a reply. And in the route reply packet, there is also the tube fields. And when the intermediate node receives the route reply packet, it will, because in the route reply phase, and the intermediate node know the contending nodes around itself, then it can calculate the real bandwidth consumption of the flow. Then it checks the bandwidth availability, and if it's successful, it reserves the bandwidth, set a timer, and forward the packet reply. Otherwise, it will drop the packet. And this route reply packet will go all the way back to the source. After this flow was admitted into the network, if the node B wants to admit flow 2 into the network, it will also flood the route request packets. But here, if we assume flow 1 already saturated the node R2, then the flow will be rejected at this node. But it can find another longer path to the destination. And now, if we assume again the node R4 got saturated after the flow 2 is admitted, then the flow 3 will be rejected and it cannot enter the network at all. So now I'll give some simulation results of our scheme. And all the simulations in our work have been done in IS2, and the max settings is 802.11 DCF, and the bit rate is assumed 2 megabit per second, and radio range and carrier sense range of a node is assumed 250 meters and 550 meters respectively. And sync buffer is 64 packets with time of 30 seconds, and the capacity of the interface queue is 50 packets. And there are two priorities of packets. The routing packets has higher priority over data packets. And first, we consider a static network which consists of 35 nodes. Neighboring nodes to neighboring nodes are 250 meters wide. So first we need to show the effectiveness of our QoS routing. That means the routing can find a path which satisfies the bandwidth. So here we start the node. We start the two flows first. The two blue flows first. One is from 16 to 17, and the other one is 17 to 18. And we adjust the traffic load so that we can saturate the load 17. So later on, when node 3 wants to find a path to 31, it cannot go through the 17 because 17 has already been fully loaded. So it will find a longer path instead of the shortest one. And second, we want to show our scheme can provide QoS guarantees to admitted flows. First, we consider the very simple scenario. The same as above experiments, the two blue flows start first, and the total traffic of these two flows is big enough to saturate the node 17. So later on, node 17 wants to admit a new flow to node 10. It will get different results with or without our QoS scheme. And we look at the following three metrics. One is throughput, average packet delay, and last packet delivery fraction. And we can see with our admission control scheme, only two flows enter the network. The flow 3, the red flow, got rejected. And in this case, low congestion happens in the network. So the two admitted flows can achieve the desired throughput. And in the right figure, we give the results without admission control. In this case, all the three flows enter the network, but the throughput changes dramatically. And sometimes the throughput goes all the way down to close to 0. And the average packet delay, we can see the scale of the y-axis of these two figures are different. So the delay with our admission control scheme is much smaller than that without admission control scheme. And also we give the packet delivery fraction with admission control. The packet delivery fraction is always close to 1, but this is not true for the case without admission control. Sorry. And in the second experiment, we choose node 17, the center node, as our destination, and 9 randomly chosen sources send packet attempts to establish a CBR collection to the destination. The flows start one after another every 5 seconds. So after 45 seconds, all the 9 sessions are active, and all the nodes, all the flows have the same traffic pattern. The packet size is set to 1,000 bytes, and sending rate is 25 packets per second. So this translates to the required bandwidth of each flow, about 258 kilometers per second. And we give the in this figure, each vertical line represents a start of a new flow. So we can see there's only 7 flows admitted in the network. The other 2 got rejected. So we can say the throughput of the 7 admitted flows matches their requirements, and also their packet delivery fraction is almost close to 1. And this is average packet delay results. Okay, go here. And also we want to show by considering parallel transmission, we can increase the channel utilization while still maintaining some level of quality of service. We consider a network which is 1,000 meters by 1,000 meters square, and there are 20 random positioned nodes, and every node in the network attempts to establish a CBR connection to a random destination, and we repeat this requirement. We repeat this experiment 50 times, each with different topology and different traffic pattern. We compare the number of admitted flows and the aggregate throughput with and without parallel transmission consideration, and we can see there are total 19 times in which more flows admitted in the network, and there are a total 31 times in which more aggregate throughput can be achieved with parallel transmission. So, and also we want to show, even though we admit more traffic into the network with parallel transmission consideration, we didn't hurt the quality of service. So in this figure, the x-axis is the aggregate throughput improvement, and the y-axis represents the packet delivery ratio of packet delivery ratio. So just if we just look at the these 2 points, with parallel transmission consideration, in total, 350 kilobit per second traffic can be admitted into the network, compared to no parallel transmission consideration. But the packet delivery ratio is almost the same, and very close to 1. So by this figure, we show that we increase the channel utilization by admitting more traffic into the network, but does not hurt the quality of service. Here we can see the most improvement happens in the 8th experiment. So in the following slide, I'll give the topology corresponding to this experiment to explain why there is so much improvement in this experiment. So this is the network topology and traffic model corresponding to the 8th experiment. And in this one, because most of the this flow is the last admitted flows in the network, and why is there a huge difference between parallel transmission consideration and no parallel transmission consideration? The reason is that most of the traffic in this network is outside of the load 14's comparisons range. So there is a large part of parallel transmission. So this is why if we consider parallel transmission, we can automate much traffic into the network. And there are 2 cases in without parallel transmission consideration. And in the first case, the number of admitted flows is the same, but with parallel transmission consideration, a bigger flow can be admitted into the network. So in this case, aggregate throughput is improved. In the second case, if we consider parallel transmission, we can admit one more flow into a network compared to no parallel transmission consideration. So the performance improvement can be represented by two different ways. One is more admitted flows. The other is same number of admitted flows, but the volume of the flows is bigger. And we import our QoS scheme into the orbit, and because current wireless cards don't support bit time measurement, so we simplify our approach. We set all the nodes to promiscuous mode, and therefore available bandwidth can be estimated based on counting the packets during the measurement interval t sub p, and also we take into consideration of all the overhead, and we can estimate the available bandwidth using this formula. Here the Li is the package size, and HPLCP is the length of PLCP header, and N data is the number of data packets, and also we use CW mean times use lot to represent the average backoff time, and the implementation is we configure the raw device in the Matter Wi-Fi driver, and to make the wireless card can hear everything on the channel. And also we wrote a monitoring program to count the packets, count the bytes, and update the available bandwidth periodically. And the operate demo setup is like this. We just consider the three parallel flows between these three pairs of flows, and then all the traffic can be sent back to the display, so we can see how good the video quality is if the QoS routing and admission control scheme is used. Now I'll conclude my work. In our work, we proposed a QoS routing and admission control scheme for wireless ad hoc networks. And in this work, we consider the shared nature of single-channel wireless communication, and also we exploit the parallel transmission to increase the channel utilization while maintaining quality of service. And also we showed the effectiveness of the proposed scheme via simulations and operate demo. And we showed the QoS routing can find a end-to-end path which satisfies the QoS requirement. Also, we show our QoS scheme can provide some guarantees to admitted flows, and also we show by considering parallel transmission, we can increase the channel utilization, but still maintaining the quality of service of admitted flows. And also we get some validated parts of the implementation through orbit demo. So in terms of future work, we need to improve the unused bandwidth estimation algorithm, because when we estimate the bandwidth of the carry sense neighbors, we use the passive approach, which is too conservative. So we need to improve this algorithm a little bit. And also, we need to design a more responsive QoS violation detection and recovery. For now, we just depends on the routing protocol, the 3-second reflection of lunar to do this QoS violation detection and recovery. We think there should be some better way to do this. And also, we need to extend the scheme to work with other QoS metrics, such as delay or delay jitter, because for now, we just focus on QoS support in terms of bandwidth. And any questions?